Hello and welcome to Void Electronics. In today's video I will attempt to repair this Telequipment D75 oscilloscope. Honestly, I don't know much about it. All I know is that I bought it from the flea market, I plugged it in and I get nothing on the CRT. And I also noticed that it has some missing screws and it is in an overall poor shape. First of all, let's talk about safety. You shouldn't try this at home because this oscilloscope works with mains voltages and even voltages that are way higher than mains voltages, in the order of kilovolts. So fixing a CRT oscilloscope like this one is a really dangerous task unless you really know what you're doing. So if you want to replicate anything that you see in this video or on this channel, you do so at your own risk. So as I said, I plugged it in before, which is not really a good idea. But let's just pretend I haven't done this. So the first thing to do is a visual inspection. And we already have some really bad signs here. First of all, you can look at the bottom panel and you can see that it is missing. I mean the bottom cover. And also the top cover is loose. This is the state it came in, so it just falls off. This is not a good sign because this means that somebody has been in here before and probably just gave up on it. But let's keep going and see if we can fix it. And also it's a good idea to look at the power cord. If the power cord is damaged, it's not a good idea to plug it in. Just replace it first and plug it in afterwards. But this is in a decent shape, I would say. Now there are a few more things that I like to check before plugging it in. And that is, first of all, the voltage selector. Here in Europe we have a mains voltage of 230 volts and this is configured to 240 volts, so I would say it's okay. You can leave it as it is or you can reconfigure it to 230. I will leave it as it is for now. However, if it were on a lower voltage like the US voltages of 120 or 110 or something like that, I would assume that somebody already plugged it in Europe and has already fried it, so I would pay more attention to the power supply section. And obviously I would lose interest immediately. And it's a good idea to check something else, which is to make sure it's not a dead short across the mains. So I will check for continuity between the two prongs, obviously with the oscilloscope on. So we have a resistance here which looks okay. And also you can make sure it doesn't have a ground fault, so you can measure between the prongs and the ground. Looks like an open circuit, so I would say it's relatively safe to plug in. So to plug it in, I prefer to use this transformer, which is more than a variac because it's an actual isolation transformer that is also variable. So pretty nice pretty nice piece of gear, I would say. So I will adjust it to around 230 volts and I will plug the scope in to see what happens. Also it has an ammeter, so we can notice if it draws any power or not. And it does. The power LED lights up. This is a good sign. Intensity is full. We can wait for the CRT to warm up. It probably doesn't, but let's pretend it does. And now we can try to get anything on the screen, which doesn't happen. We can press trace locate, vertical position, I don't know, horizontal position maybe, or a combination of the two. Focus. So there are two things that could happen here. We either have a missing voltage for the CRT or the CRT is dead. So w140.com saves the day once again because I found a schematic there and it looks like the CRT is powered by one of these circuits like this. So it's a DC to DC converter. It's not really powered from the mains transformer and this whole thing looks like a blocking oscillator to me. So if I understood the schematic correctly, this is the primary winding, this is the feedback winding for the oscillator, and these are two secondary windings. So what basically happens is that power comes here. It's, I think, from the plus 30 volt rail, which comes from the mains power supply, I guess. Power goes into the primary, and the second terminal of the primary goes into this power transistor. Now, to make this thing oscillate like a blocking oscillator, we have feedback which comes from a separate winding, and as you can see, it feeds back into the base of this transistor to make it oscillate. Now, if you look at the second terminal of the feedback coil, it is not referenced to ground, and that's because we have some sort of feedback here to regulate the high voltage, I guess. So all the things that we see here are part of the feedback loop, and unfortunately the feedback loop here closes through some things that are on different pages, so you don't see the full loop. But you have here an adjustment which says set 2.5 kilovolts, so probably minus 2.5 kilovolts. I'm not sure, the schematic is barely readable. So yeah, I suppose that this is basically the error amplifier to make the whole thing regulated. So this is where we need to look first, and maybe test the CRT as well to see if the filament is open or not. But I suspect there is something wrong with the high voltage power supply. Let's see if I'm right. So to access the power supply and the CRT, we need to remove this cover first. So as Shango66 would say, this is baked. And it even comes with a factory spider web. That's nice. To make things worse, it even has two wires that go nowhere. So we have this wire, which somebody terminated like this, and another wire, the same color, terminated like this. So I'm not sure, maybe something was removed from the back panel, or who knows. Once again, not a good sign. Honestly, I don't like the way the high voltage power supply looks. I'm not sure about these two big capacitors there, they looked kind of baked. I'm not sure if they're supposed to be black in the first place, but yeah, we'll see about this. Now I will try to remove the CRT socket, and before doing this, just to be safe, I want to short out some things to make sure it doesn't shock me. So I have one of these wires with alligator clips. I will connect it to the chassis, and I will short out the things that look high voltage to me. So first of all, the heater runs at minus a few kilovolts. I'm pretty sure these are the heater wires. This looks high voltage to me as well, probably focus or something, not sure. We can short out everything, I guess, just to make sure it doesn't shock me. Obviously the scope is unplugged. Now I think we are safe to try to remove the socket, which I'm really reluctant to do. I hope I won't damage anything, including myself. And let's see. Okay, that was easier than I expected. So I'm interested in the integrity of the heater, first of all. So the heater is between pins 1 and pin 14, so they're here and here. Let's test them. And we have continuity, so the heater is okay. Good news. The next thing to do is to test for the heater voltage, which is something that I'm once again very reluctant to do, because the cathode runs at around minus 2 kV or something like that. So I'm not risking my keysight meter for this. So I'm using this old analog multimeter on the 10 volt AC range, and I managed to attach some clips there because there is no way I'm touching this while it's on. Let's start it and see what happens. Okay, looks good. So we have heater voltage here. The only thing is that I'm not sure if the heater voltage comes from the high voltage power supply or from the mains transformer. In any case, we have around 5 volts. I'm not sure if it's the right voltage, but it probably is, and we have some smoke. Okay. We have pyrotechnics as well. That's weird. I think the smoke comes from there, so let me give you a close-up on the pyrotechnics. Yep. The thing is that I'm not sure what that entire board does, but we'll find out about that. So this resistor is smoking, I think. And I'm so sorry for you guys that I cannot share the smell because the apartment smells amazing right now. So I kept thinking how to check for other voltages around the CRT, and I want to have a look at the cathode voltage as well. So I will use the old meter once again because in theory it goes all the way up to 2.5 kV, and I connected the positive probe to the chassis and the negative probe to the cathode, which is pin 2 on this CRT. Let's see what we get. And we get nothing, so maybe the high voltage power supply is not working. So by having a closer look at the power supply, it looks like the heater is powered by the mains transformer. So the fact that the heater voltage is correct doesn't mean that the high voltage power supply is working. So since I wasn't sure whether to investigate the smoke or the missing high voltage, I decided to have a closer look at the manual once again to find out what this board is and why it could be smoking. So this board is what they call a PC128 or the bright up board, which is the board that modulates the grid voltage of the CRT, which in turn modulates the brightness of the beam. And this board is connected to a section of the high voltage power supply that produces the grid bias, so the issue that we're looking at could be related to the smoke that we saw on this board. And also this resistor doesn't look factory to me because I can see some cut traces there. So I think the next step is to check all the main voltages produced by the linear power supply, because this could probably lead us to the failure. So to do this, I had to look at the manual and I identified the linear power supply, which is this bottom CRT that we have here. Is right in the rear part of the oscilloscope on the bottom. And in the manual there are some notes about the voltages that you must have at each pin. So I assume that these are the pins that I have to check. However, I was wrong because apparently these are all the inputs that come from the mains power transformer. These are not the outputs that we are supposed to check. So after looking around some more, I noticed that in the manual it says something about a connector. And apparently this is the connector that they are talking about. So this is the connector that connects the linear power supply to the main board. And the manual also mentions the voltages that we are supposed to have at every single pin. So let's test those voltages. First of all, every second pin should be ground, and we can check that with a multimeter grounded to the chassis. So the top one must be pin number 8, and it is grounded. The next one is pin number 6, which should be ground as well. Then pin number 4 should be ground as well, and it is. And then pin number 2 should be ground as well, and it is. Now we can set the meter to DC volts, power up the scope once again and measure the other rails. The first rail is the plus 30 unregulated. We have 27 volts, so that's okay. The next one is on pin 3 and it should be plus 24 and it's spot on. The next one should be 105 on pin 5. 1, 2, 3, 4, 5. It's 80 volts, so there is something wrong in here. And the next one should be plus 24 on pin number, minus 24 on pin number 7. And it's spot on, so we have an issue on the plus 105 supply. So after some more digging, I managed to identify the smoking resistor on the actual schematic. So let me show you how I did that. First of all, that's the smoking resistor. And I noticed by looking on the other side of the board that it is connected to a transistor. So this is the transistor where the resistor goes, and the resistor goes between the third pin of this transistor, the lower one, and ground. And apparently the lower pin is the collector of this transistor. And by looking at the silk screen, we can see that this is TR355. And this is how I identified the resistor. And apparently it is factory, it was just bodged in there. So the resistor that's smoking is this one on the schematic, which is R368, and the entire circuit looks like the output stage of a class AB amplifier. And the amplifier is powered by the 105 volt rail. So maybe the issues that we've seen so far are somewhat connected. So the first thing to do is to remove this transistor from its socket and test it. Let's use the Chinese tester for this, so the moment of truth. Why does it take so long? Okay, no unknown or damaged part. That's not a good sign. Not sure if you can read the display, but that's what it says. Maybe it's better now. Honestly, I trust the Chinese tester a lot, but just to be 100% sure, I want to test the transistor with a multimeter as well. So this is a PNP transistor, and the pinout is right on the transistor, but the text is too small to see on video. So it's EBC in this order, emitter base collector. And since we know this is a PNP, the internal junctions should look something like this. So it should have a junction from emitter to base and another one from collector to base. Let's just test the internal junctions to see what we get with the multimeter. So the positive probe goes to the emitter first, and the negative probe goes to base. We have about 500 and something millivolts, which is a bit low, but let's say that's okay. Let's reverse the probes to see if the junction conducts in reverse. It shouldn't. And it does. We have exactly the same voltage, so this junction is basically a resistor. Next one, we should have a junction from collector to base. The voltage should be around 650 millivolts or so. It is 100 and something millivolts, so this is definitely not good. Let's reverse the probes to see what happens. And we have exactly the same voltage, so this is basically a resistor as well, which means that the transistor will conduct from emitter to collector as well, which shouldn't happen. And as you can see, the transistor conducts, and I'm pretty sure this happens in both directions. Let's reverse the probes once again. Yes, so basically we have two resistors inside, which means that the transistor is dead. So to be honest, I was almost certain that the transistor is dead, and this is the reason why the resistor is smoking. So at this point, I'm really curious to see what happens with the transistor out. Do we get a trace? Honestly, I'm not so confident about the rest of the circuit, so I expect some other components around the bad transistor to be bad as well, but let's just plug it in, just for fun. I'm curious if we get some more smoke. Okay, we are at full brightness. The position of the focus pot doesn't really matter. Trace locate doesn't do anything. Position. Position doesn't do anything. I don't know. Horizontal position. doesn't do anything. Trace locate. So it's still dead, but it's less dead than before. So I think it's time for some more probing to see why the bright up board is not brightening up. The next aspect would be the other transistor in the complementary pair, because since we had an overcurrent through this part of the circuit, I'm not that confident that this one survived. And also we have some discoloration on the board, which means that it got crazy hot at some point, which also indicates that there are some other issues with this board probably, because the discoloration is not in the area of the bad transistor. So this is TR354, the upper one. Okay, believe it or not, it's still good. I did not expect this. Let's put it back. Now let's check the driver transistor as well, which is this one, TR353. So this is TR353, or the driver transistor. And it tests good. So what I did off camera is to test every single component on this board, and apparently all the other components test okay. However, I had a really hard time finding the PNP transistor. That's because in the service manual it calls for a transistor that I've never heard of. So TR355 it has an internal part number, something like 151 whatever, and it has, I guess, an external part number as well, which is TO203, and by googling it I'm out of luck. The only thing I could find is unofficial information on some forums where people wonder what to replace it with, so I don't know. I guess it's something relatively high voltage, relatively high frequency. People said it should be replaced with something that has a transition frequency of around 200 megahertz or something like that. So I did my best to find something in the junk box. I was out of luck, basically none of the transistors fit. So I took a trip to the local electronics store, and I'm so glad we still have it. And I got some transistors that could work in this circuit. And since local electronics stores are dying pretty much anywhere, I decided to buy all the vintage transistors that they had in stock, just in case. So the replacement transistor tests okay, and I will just plug it into the board to see what happens. Let's hope the oscilloscope doesn't fry this one as well. Actually, I took some precautions and I measured pretty much anything that I could measure around the grid circuit. So I tested for shorts between the grid and the cathode, between the grid and the focus electrode, and I also tested the diode and the power supply that generates the grid bias, and everything tests okay. And to make things annoying, the replacement transistor obviously has a different pinout, so we have to twist the pins just a bit. Another weird thing that I noticed here is that the wire that goes to the grid bias supply broke off. And I'm not sure if I broke it when I twisted the board or if it was previously broken before. Because if it was previously broken, then that explains lots of things. So with the replacement transistor in its place, let's fix the grid bias wire and give it another try. And to fix the wire, I will use the staple of Romanian electronics, which is this soldering gun. This is probably as old as the oscilloscopes, so it is age appropriate. First of all, I will use some rosin to prepare the wire for soldering. Then I will apply some solder on the wire. And I will do my best not to make the wire a lot longer, because this is shielded and is not supposed to go for long runs in an unshielded manner. I will prepare a piece of wire in the same way. It's not really the proper wire, it's something that you normally use to connect your washing machine, but whatever. Okay, let's join the ends now. Okay, and now I think the wire will be easier to work with. Now the next step is to insulate the solder joint. So I will use some heat shrink for this. And I will use the heat gun. And I will use the heat gun to make the heat shrink shrink. It's on the lowest setting it can go, which is 150 degrees Celsius, by the way. Now I'll try to solder it back onto the board. So we have a hole here that was probably plugged by the previous wire. I will try to unclog it first and then we'll see where this goes. So to do this, I will attempt to use this solder pump or vacuum pump or whatever you want to call it. Okay, that didn't work. I don't have enough hands for this. Let's try again. That looks better. Now let's try some solder wick as well. Maybe this will work better. I don't know. Okay, so it looks like the hole is unplugged, at least partially. Let's see if the wire fits in. And of course it doesn't. So I guess I will just take advantage of the hole that we have next to the resistors. Just feed the wire through there and solder it on the other side. Something like this. So I know it's not ideal, but we have bigger issues than this. Once again, we have the same recipe here, some rosin flux, some solder, let it stick to the wire. And then I will use the tweezers to try to press the wire in. Okay, that looks decent. Let's just hope it doesn't short out on the ground plane. So with the bright up board back in its place, I will give it another try, and I'll be honest with you, I don't expect the scope to work, because if I understood the schematic correctly, I don't think that the faults that we've seen on the bright up board can cause the high voltage to stop working. But anyway, place your bets now. Basically, I'm curious to see whether or not the circuit will blow the transistor once again. So I will start it up, look for smoke, and then I will test the transistor that we replaced once again. So place your bets now. No smoke yet, but no high voltage either. Okay, so let's press some buttons at random to see what happens. Trace locate, nothing. We are at full intensity. Focus doesn't really do anything. Horizontal position, vertical position once again. Yeah, I think we have no high voltage. Okay, let's test the transistor once again. So I removed the replacement transistor from the oscilloscope, and now is the time to place your bets on it. 3, 2, 1. Okay, it's still a transistor, so this means that we have a less dead oscilloscope. And now with the clips attached to the output of the bright up circuit, I want to test if we have any DC voltage at the output. And we do, and we even get some repetitive pulses, which means that the bright up circuit is probably working. Okay, so we've made some progress, and I think it's a good idea to look at the signal on the oscilloscope as well. So once again, I don't want to risk ruining my Siglent oscilloscope with the high voltages that we have in this oscilloscope, so I will instead test the signal with an age-appropriate Tektronix 466. We are on channel 1, AC, coupling, 5 volts per division. Let's see what happens. Okay, maybe the signal is lower than this. Actually, it works better if you turn it on. Okay. Now this is weird. So we have some pulses, but we have some huge ripple as well, and I'm not sure if this was supposed to happen. Probably not. So as you can see, we have some pulses there as described in the manual, but they're riding along a huge ripple, so maybe we need to check the power supplies as well. We are at 1 volts per division, so we have a ripple of around 2 volts peak to peak, which is huge. I think it is unacceptable. So the power supplies definitely have some ripple. I checked all of them, and the ripple is in the order of tens of millivolts on every single supply rail, so the ripple is pretty high, but I don't want to investigate it at this point because I want to see the high voltage working first. So let's look into that. Now for the high voltage to work, we need a few things to happen. First of all, we need to make sure that we have plus 30 volts both here and here into the primary. We need to make sure that this transistor is okay, that this diode is okay, and to make sure that we don't have any open windings on the transformer, because if we do, that's pretty much game over for this oscilloscope. So to check for the plus 30 rail, my plan is to follow the wires from the transformer back into the PCB, because on the PCB the connections are numbered. And basically I'm looking for connection number 3 and connection number 5. And connection number 3 should have 30 volts on it or thereabout. So I found the wires. I'm just not sure which one is number 3 and which one is number 5, but I guess they both should have around 30 volts on them, so let's see. And sure enough, we have around 1 volt here instead of 30. And on the other one we have 200 millivolts instead of 30, so something's definitely wrong here. So after another careful visual inspection on this board, I found one of the issues. And one of the issues is this component right here, which is exploded basically. And you can also see a discolored resistor underneath it. So by looking at the schematic and on the silk screen, I identified the discolored resistor, and it is R310, and it has a thermistor across it, which is the part that blew up here. And the plus 30 rail comes through these components, so it makes sense to have a low voltage. However, now we have to check for shorts on this rail. Otherwise, in case of any shorts, these components will blow up once again. So I'm checking for shorts on both pins of the blown out thermistor because I'm not sure which is which. Let's start with the left one. And it's not shorted, it looks like a capacitor that's charging up. And the right one. This one is also not shorted, it also looks like a capacitor that's charging up. So this looks promising. But before applying power to it, I would like to check the power transistor and the diode that's near it. So place your bets on the power transistor. Okay, this one is good, I will put it back. So with the transistor out, I will also check D302 to make sure it's not shorted or open. To do this, I connected one probe to the chassis, and I will attach the other probe to the transistor emitter basically, but with the transistor out. And it looks okay. Let's swap the probes really quick. And in reverse it looks okay as well. So the diode is also good. And now, using some dentist tools, I managed to maneuver the transistor back into its socket. And yes, I know these are not the proper tools for something like this. The important thing here is to put the mica insulator back in its place, otherwise we will get some fireworks. So I'm pretty sure that power comes in on this lower wire, let's check. And it does, we have about 26 volts. And it was supposed to go through a resistor and a thermistor. So my plan is to lift this wire and apply power to the other terminal of the thermistor from an external power supply to see if the high voltage power supply runs. I also checked the transformer, and both the primary and the feedback windings look like a short almost, so I'm not sure if that is supposed to be like that or not, but since there are a million things that could go wrong with the high voltage power supply, I plan to just power it up from a current limited power supply and see what happens. So I will limit the current to around 700 milliamps. I'm not sure about the current consumption of such a thing. And I will set the voltage to around 25 volts. I'm not sure what the voltage is supposed to be there, because we definitely have some voltage drop across the resistor and the thermistor. Okay, let's leave it like this. And now is the moment of truth. With the scope powered up, I will try to apply power to the high voltage power supply. And I also raise the camera to catch any pyrotechnics that could happen on the way. Let's see. Okay, 300 millivolts, maybe 300 milliamps, sorry, so I guess it works. I'm not sure about this. Let's try to do anything with it. Trace locate doesn't do anything. I don't see any smoke yet. We are at full intensity. Focus doesn't do anything. Position. Okay, this is disappointing. I did not expect this. I actually expected it to be a dead short or something like that, even if I checked for shorts. But now, maybe the high voltage power supply runs and for some reason we still don't get a beam. So now, with the high voltage power supply presumably working, my plan is to check once again for high voltage on the cathode using my old sacrificial meter. Let's give it a try. Okay, we definitely have some high voltage there now, so we've made progress. Now I'm not sure whether or not to rely on the reading that I get on this meter. I'm not even sure how to read it because this one is a bit confusing. So I'm not sure whether or not this is the right voltage, but I'm sure that it is regulated because I can vary the input voltage a lot and the needle barely moves. So the power supply is doing something, it's probably regulating. So once again, with a sacrificial meter, I will try to check if the voltage is above 500 volts. Maybe this is not a good idea, but let's give it a try. We are on the 500 volt scale. And it's not, unfortunately. It's about 400 volts or so. So we have a low high voltage. Since we have an adjustment on the cathode voltage, I think it's a good idea to try to adjust it, even though I don't think we have that much range. So let's see if it changes anything. Okay, it does change something, but the changes are minimal, so we definitely have a fault in the high voltage circuit somewhere. So let's try to measure G1 as well. Maybe it will help us get an idea of what's going on. So G1 is really high impedance, so maybe this is not the most scientific way to test it, but let's give it a try anyway. Okay, so I think G1 is supposed to be at around 2.5 kilovolts as well, so it is once again very low, around 400 volts as well, so it looks like it sits at the same voltage as the cathode basically. So in my opinion, there is a chance that the high voltage multiplier is broken, or there is something on the high voltage section that drags down the entire power supply. So what I did was to remove the quintupler or the high voltage multiplier from the transformer, and I want to redo the measurements for the cathode voltage and the G1 voltages to see if they go back to normal. Here's a close-up just to see what I'm talking about. So I disconnected this wire from the transformer. Okay, so the moment of truth. Is the high voltage multiplier dragging down the entire thing? Let's see. And it is, unfortunately. I don't know. It's good news and bad news at the same time. Good news is that we found a fault. The bad news is that the high voltage multiplier is a pain to replace. I don't know how to replace it. So we have huge cathode voltage right now, but it's going down. So maybe we have other issues as well. Not sure. This is weird. Let's measure G1 as well. Now we're connected to G1. 2.5 kV, I mean minus 2.5 kV with respect to the chassis, so yeah, the voltage is right. By the way, let me give you a better look at the meter. Maybe you couldn't see it in the first shot. 3, 2, 1, fire. So it goes full scale, so we have at least 2.5 kV, minus 2.5 kV. So since this video is getting really long, I would like to end it right here. Unfortunately, this is a failed repair so far. However, I think there are some nice takeaways from this video, which is the overall troubleshooting strategy whenever you're working on something, and also that you shouldn't invest a lot of time and money into something that is probably not fixable. So I know that some of you like to start by replacing every single capacitor and cleaning up everything, but in this case, I'm not entirely sure if this scope is fixable. Anyway, if you'd like to see a follow-up, or if you'd like to see me repair the multiplier, or maybe get a new one, or maybe do an autopsy on it in a different video, please let me know in the comments. And also, if you like this video, please give it a thumbs up. And if you want to see more repairs and projects related to electronics and programming, please subscribe to this channel because there is more content like this on the way. That's it for now. Bye.